All right, good afternoon, everyone. Thank you for joining us in the review session for the RC design class. I'm currently in my office right now, so if you want to come to see me after review, feel free to do so. I'll stay in my office tonight till 7:30, 8-ish, and before running home. So if you need any help tonight, you can also reach me through email. A quick update, I'm getting there in terms of grading homework number 2. I hopefully finish that tonight or tomorrow morning, and I'll start grading number 3. So latest tomorrow noon, hopefully tomorrow evening, I get everything done. But from what I see, there are not a whole lot of mistakes from the homework. I guess most of the problems are homework number 4, but I have a few emails on Monday asking me to do the extension on homework number 4, which I did for another day. So that means I cannot get homework number 4 graded and return to you before the exams. Okay, so unfortunately that has to be the case. So if you need any help on homework number 4, send me email. Okay, and let me know. I can help you. If you have trouble like right now, you can come after the review session. I'm in my office. Like I said again, I'll be here till 7:30 to 8 p.m. So you can still track me down. Okay. All right. Without further ado, let me start sharing my screen. So hopefully you can see that. Let's see here. Okay. Give me 1 second. I think I need to do a different. Okay. Web link to be able to do that. Okay. Jesus. Okay, MST. So if I do the share screen and air. Sorry, folks, give me 1 second. Okay, let me see what's going on with this. Every time I do this on campus, somehow I couldn't share my screen. Okay, give me 1 second. Cable share. Finder. Trust. Okay. All right, good deal. Okay, so I think you guys will be able to see it. So let me share my screen. So can you guys see the exam?
Yep.
Okay, good deal. Okay, so this is the past exam problem set I have on Canvas. Okay, and to be precise, this is set 2. I uploaded 2 sets, but there's some tiny mistakes in the first set. So the second set is like a corrected version, but there are some problems are essentially the same, but which is number changed. Okay, so you may want to take a look at both and compare your notes and catch some tiny things. Okay, but anyway, let's just start going through them. So first question, the stress distribution in a concrete compressive zone used for flat sheet design in accordance with ACI318 code can be represented by an equivalent rectangular concrete stress distribution, Whitney stress block. Now we know that, right? Whitney stress block, and with a height of what and magnitude of what. So immediately in your head, you should start thinking, and sorry, let me just change my line width. Okay. Okay, this is better. All right, so you start thinking the line distribution of a concrete compressive zone, and this is 0.85 F prime C, and this is the effective zone A. Okay, so here it was asking the height of what, right? The height of what? The height of beta 1 C, right? Beta 1 C, right? So now C is the actual compressive zone, right? So we really don't have any control of it, but we have a beta 1, and you know that beta 1 is a function of the compressive stress of prime C, and precisely it follows, actually reverse way. It follows a line like this. Okay, and so the lowest value is 0.65 and highest value is 0.85. Okay, and now you look at that, you take a look at the choices I have, right? So A is always 0.85 times C, which is not right. Give me just 1 second, okay? You're for the review, right? Yeah, I'm doing it online right now.
Okay.
Can you see it?
Yeah.
If
I
not, you
didn't
can,
try.
yeah, you can join.
Yeah.
So I
I
got,
think there's more people coming in.
okay, turn on the lights. Can you help me? Thank you. Okay, so you can leave the door like unlocked and people probably can walk in. So folks, I have some people join my office, but the same thing. Nevertheless, we can do this together. So as we were talking about the first problem in the exam number, one from the sample problem. So we know that the effective compression zone A equal to beta 1C. Now beta 1 is actually a function of F prime C, right? So you look at the choices, number 1 is always 0.85 times C. Definitely not correct. Okay, so goes with B. So none of A and B is the correct answer. So C depends on F prime C, right? So yes, it definitely depends on F prime C. D depends on F prime C. So this is both are okay. Now the second part is with the magnitude that, right? The magnitude is always 0.85 F prime C or depends on F prime C. So from the Winnie stress block, we know that it is always 0.85 F prime C. Okay, so if I want to write down, this is what it is, right? So definitely the correct choice should be C. Okay, now the second problem, the compressive strength of the concrete is determined by means of what and tested in accordance with what. So take a look at the choices, right? Cylinder loaded in the cross section with a uniform pressure on the cross-sectional surface of the cylinder, ASTM C39. Cylinder loaded on their side on the uniform line load along the length of the cylinder. So if I start drawing the first one, I have a cylinder loaded in this way, right? And the second one, I have a cylinder loaded in this way. So the first one seems like a compression test. The second one seems like a split cylinder test, right? Number 3, C, beams loading and bending. So this is a beam bending, right? You have seen that, right? Beam bending. And D, cylinder loading in the cross-sectional uniform pressure on the cross-sectional surface cylinder and ASTM C496, right? C496. And now A and D are same, except that ASTM standard is different. All right. Now E is cylinder loaded on their side with a uniform line load along the length of ASTM of the cylinder, ASTM C39, which is definitely not right because this is split. Right? This is split. So yeah, sorry, I couldn't get a room. So my guys have to squeeze me in. So okay. And get more chairs maybe, or you have to. Can't get more
I can
chairs.
sit on the ground too.
No, don't do it. Do you see any chair from the classroom? Or
We'll hunt down a chair.
okay, I
We'll
take
need-
my chair. So you just need one, I guess. Okay. All right. So I can do this.
Is this the first review? Or
Yeah,
the
it's
second?
the second set of problem. Yeah,
Okay,
yeah.
that's what I was
Yeah.
working on.
So now we're taking a look at the E, and E is a split cylinder. Yeah, that doesn't move. It's broken. You have this. You might have the stuck there. Sorry. So it's a line distributed loading, which is again the split cylinder. F beams. So we're talking about beams here. Okay. Now the problem is asking the compressive strength of the concrete. So that is F prime C. So naturally it has to be either A or D. Now there are two standards, C39 or C496, and I'll go with 39, right? So that is my correct answer. Okay, so this is not right. All right, so second is A. Now 3, which of the following statement is true? A, the yield strength of reinforcing steel in tension is higher than the yield strength in compression. Is that right? No, right? This is not right because for the steel, it is symmetric. It is symmetric. All right. Now B, the yield strength of the reinforcement, the yield strength of reinforcing steel in tension is higher than the yield strength in compression. Of course, this is not right, right? Because it's symmetric. This is symmetric, right? Oh, go ahead. Oh, you got it? Okay, thank you. So now, with that being symmetric, again, this is not correct, right? So C, the modulus of elasticity of reinforcing steel in tension is higher than the modulus of elasticity in compression. Again, the symmetric, right? So now, without even thinking more, your natural choice is D. Okay, natural choice is D. All righty. So number 4, the purpose of the strength reduction factor phi is account for what? Where the purpose of a load factor is to account for what? Now, here, phi is a strength reduction factor, right? So definitely under strength of the member. Is that right? But again, the importance member still here disturbing, right? So maybe this one, maybe this one, maybe this one. I'm not sure, right? So I guess the answer is really on the second one, where the purpose of load factors count for what? So definitely it's count for the variation of loads during the life of the structure. Is that right? Variation of load during the life of the structure. So for that, you can select A. Okay, select A. So A is the correct answer. B and C and D are not right. Okay, all right. Here, number 5 are calculation problems. Now, sorry, I need to mute somebody. This is second set problems. Okay, and now for this problem, since it's a calculation, I will not go through the detail of calculation. Okay, and I don't have the correct answer for them. You need to find it for yourself. All right, but I want to give you a rationale, the approach of how you can find them. Okay, now first of all, the cracking moment of RC section is what? So how to find the cracking moment? So when we talk about cracking moment, it is always talking about cracking moment for a unreinforced section, meaning just the concrete block. So old friend, we have a pure rectangular section that the width of it is 14 inches and the height of it is 20 inches, sorry, 22 inches. Okay, so to get the MCR, we just need to use modulus of rupture FR and moment of inertia for the gross section, which is I, divided by the distance YT. Okay, now a lot of folks asking me, what is YT? Now YT is a distance from the tensile fiber to the neutral axis of the section. Now with this being the rectangular section, neutral axis right in the middle. Okay, and that's why YT is half of H, which is 11 inches. Okay, now FR is just modulus rupture, so 7.5 square root of F prime C, and in this case, M prime C is 7,000 PSI. So I got 7.5 square root of 7,000 PSI. Okay, you should get roughly 500 or 600-ish PSI of a tensile strength. So save your calculations. And then I, moment inertia, has to be 1/12 BHQ, and that is 1/12. B is 14 inches, and H is 22 inches to the power of 3. Okay, and you got some number. Bring all this number in, and don't forget the YT equal to 11 inches. You should be able to find these numbers. Now, I got people find the number is 46 or something. Okay, 46.2 kip fit. Now, I think that might be an error when we change the section sizes, because it was before, I believe, 20 inches or 24 inches, can't remember, okay? But in the exam, if you have a situation like this, pick the closest, right? So, and I'm add that to the exam that you see tomorrow. I just add that this morning, matter of fact, okay? So among all these answers, C is the closest. So we'll select C, okay? All right, now effective depth of the section is what? So this looks like it's trying to find the depth, but essentially trying to find a center for the group of the bars. Okay, center of the group of the bars. Okay, now you know how to find the center of the group of bars, right? Use our sigma AI, DI, or YI. Okay, let me just clean this up. AI, YI, and divided by sigma AI, you can find the distance. Okay, and after you find the Y bar, then D is essentially H minus Y bar. Okay, so you can take a look at it. And my calculations 18.65 were close. Okay, could be wrong. Check me, okay? I could be wrong, check me.
Do you not care about the top balls?
I don't care about the top bars, okay? When I say depth, that again, depth is defined, the distance, let me write down here, from the extreme compressive fiber in concrete. okay, to the center
This is,
of the
Yeah.
tensile reinforcement. Okay, to the center of the tensile reinforcement. Okay, so that is the definition. I may be wrong, okay? I just did this fresh calculation this morning, so I could be wrong, okay? Double check me, but the process should be the same. All right, now the next one. If the maximum aggregate size is 1 inches, immediately when you see that, you start thinking about the distance or spacing between the bars, right? Especially horizontal spacing between the bars. And this has to be the largest of 1 inch dB or 3/4 the aggregate. Somebody is magnifying my noise is good. Okay, no worries. So that here, in this case, the aggregate is 1 inch. Okay, so why do we need a spacing? Because now, once I have the spacing, I can find out the minimum beam width, right? So here, I know this has to be 1 dB or 4.3 multiplied 1 inch. And dB here is what? Number 9 bar, right? Maximum diameter number 9. So I'm talking about 9.8 comparing to 3.4, right? So which one is bigger? Of course, 4/3 is bigger than 9/8. Is that right? So I have this established. So the largest is 1 1/3 inch of spacing between the bars. Okay, so you have that. Now you have number 4 stirrups, need to add the stirrups, right? And there's a gap. Don't forget when the detailed calculation comes out. Now the critical thing is that it says this beam is part of the floor that is not exposed to earth or weather, means interior exposure. Okay, interior exposure. And now if you take a look at the table we provided you on Canvas, you should be able to find the concrete clear cover is about 1.5 inch or 2 inch. I cannot remember, but you can find it, right? With that, you can do the calculation, find out the beam width. Now, I don't know which number is right because I haven't done this part myself this morning, but you can find it out. Okay. Now, if you're not sure about this, you can use table A5, but be careful. There are certain criteria to satisfy before you use table A5. And now we have number 4 stirrups. So make sure that is okay to use table A5. Okay. My suggestion is you don't use table A5. Always do hand calculations. Okay. And the reason for that is I made the problem. So I know you cannot use table A5. Okay. So I hope you're happy for this tip. Okay. Free tip.
So always calculate beam in.
Yes. Okay. So matter of fact, I can leak you the information now. Well, it's not leaked, it's recorded anyway. Now, problem number 2 is going to be detailing. Okay. Problem number 2 is going to be detailing. That means minimum beam width, spacing between bars, effective depths, so on and so forth.
Do we use hat?
Yes.
Okay.
Yes. You got to go back to your notes if you forgot how to calculate S hat and how to get that spacing.
Yeah.
Okay. Yeah. All right. Good deal. So with that, moving on. So remember, we have 2 hours and we have 4 problems. So the name of the game is actually not moving too fast. You got to think, okay, because you have enough time to finish the problem, but probably not enough time to revisit them. Means checking, right? So you want to do it right once, not twice. Okay. So here you look at this problem, and I can tell you this problem will be our problem number 3 in exam. But be careful, okay? This is the simply supported beam. We may not have a simply supported beam in exam number 1. Okay. Now you think about, right, what Bob has talked about so far in the lectures. Bob loved simply supported beam. Whenever there's an opportunity, he used simply supported beam. And Bob also likes this handover, right? Continuous beam. There's a handover portion of it, right? But most importantly, Bob loves cantilever, right? Why I love cantilever so much is because if I do a cross-section cut here, you know that the reinforcement intention is going to be on top. Is that right? Okay. Now, fortunately for this practice set, it is simply supported, meaning the tensile reinforcement is here, the 3 number 10 bars. Okay, but be careful in the exam. If you see a cantilever and I'm showing this, then the real tension bars will be 2 number 9. you got to flip the section. Okay, tricky. All right, so be careful about it. Okay, be careful about it. All right, but all these tricks aside, if you look at the section, right, what we're trying to do is do analysis of doubly reinforced section. It's not a design, it's doubly reinforced the section. The dimension of the section is given, the reinforcement are given, so essentially just need to find the moment of resistance. Okay, so how to find a moment of resistance? We have the concrete compression 0.85 F prime C, A, B. We have the steel reinforcement, that is AS, FS. Okay, and be careful on the concrete side, right? Because there is a minus 0.85 F prime C, AS. Okay, we have to dig the steel out. If you forgot, go back. Okay, dust off those lecture notes on doubly reinforced section. You probably haven't seen this for some time now. Okay, you need to review that. And remember, if we do that, we end up with a table that we have to keep trying different C. When I say different C, that is the the actual compressive zone size. Keep trying it until you reach the balance that the tension equal to compression. Okay, remember? Okay.
Within a certain margin, right?
Yes, that's the margin of error come in play, right? So here we said at least 3 iterations. We told you already. Okay, so you got to change 3 times at least to see to show me that you converge. Okay, you'll be able to balance compression. Okay. Interesting noise, Drew. And I will appreciate that, but it's in recording, so I have to mute you, okay? Now, that is 2A, to iteratively find C and find the moment capacity Mn, okay? Now, here, we are asking you guys to compare the reinforcement provided with the minimum reinforcement. Now, here, there's a trick embedded. What trick embedded? Now, in our section, the tensile reinforcement is at the bottom because we're talking about the middle span and it is simply supported. Okay, so that means tensile reinforcement at the bottom. So when we talk about compare the minimum reinforcement, we mean compare the tensile reinforcement only, okay? So it is AS, not AS prime. Okay, so when you compare, you use AS. That's first trick. Okay, be careful what we're asking you guys to do. Second trick, you look at this AS min here, there are 2 equations for it. One is 3 square root of prime C BWD divided by Fy, and the other is 200 Fy divided by Fy BWD. Okay, so be careful, has to be the larger of the 2. Larger of the 2, okay? So select well. Don't forget one of them, okay? Remember both. You calculate both, pick the larger one, okay? Pick the maximum one of these 2, okay? All right, okay, so again, just be careful with this, okay? People can get the wrong numbers on this problem. Question.
Would DS in that case be the 22 since it's from compression to tension?
22 plus the 2.5. 22 is the distance between reinforcement, right? You got to add the concrete cover because it's from concrete to tensile. Now, here, if I say that scratch this simply supported conditions, and I show you a cantilever, so the DS would be what? If I show you the cantilever, let me clean this up. Okay, if I show you the cantilever, that means, and let me just exaggerate so you know what I'm talking about. Okay, if I have a cantilever and I show a section like this, then the DS would be 22 plus 2.5 still, but it is this way. And the AS now in this case is the 2 number 9, and that equal to 2 inch squared. Now here, then in the cantilever case, this will be AS prime. Compressive reinforcement, right? So be careful. And C, compressive zone got to start from the bottom, not the top anymore. Okay, tricky, eh? So that's the game I like to play a lot. Matter of fact, all professors in concrete design like to play a lot. Okay, because sometimes cantilever turn into simply supported, turn into handover, and the reinforcement has to go up and down, down and up. Okay, so got to be careful on this. All right, so pay attention to the problem before you start working on it. That's what I mean by you don't have a whole lot of time to make mistakes. Think twice, right? Do it once. Measure twice, cut it once. Okay. All right. So let me clear this up and avoid any confusions. But again, do your calculation. If you want exchange number with your friends, that's fine. But I don't have keys to this set of problem. I just did some rough calculation this morning. So I'm not the best person to provide you the number, but I can look through your process and help you if you need to, okay? So show me your work if you want to, I can help you to spot some mistakes, okay? All right, so last one, not least one for this problem, determine the value of phi and verify whether the design flexure strength is adequate. So phi is just simple, right? For doubly reinforced section, right? You have you have actual compressive zone C, and you have the CU 0.03, and you have the depth ds. You can find out the strain in the steel, and see that it is bigger than 0.05 or smaller than 0.05 or bigger than 0.02 or smaller than 0.02. And now phi, remember, it is epsilon T, not epsilon S. See, so be careful, okay? I just made another mistake, cost myself 5 points, right? So be careful what am I talking about, it's epsilon T, okay? So don't let that confuse you, right? So it's actually epsilon T, okay? All right, phi is related only to epsilon T, which means the last layer, okay? Now, in the exam, as kind as I am, I will provide only one layer reinforcement for you in top and bottom both. So make your life easier. Because in that case, epsilon S equal to epsilon T, so you don't have to worry about it. Okay, but in real life, sometimes you're not so lucky. Okay, so be careful. Now, with that, phi versus epsilon T, what we said before is that if I have high yield strength is 0.9, low yield strength is low strain 0.65. And the cutting line is 0.02 and 0.005. Okay. All right, in between, linear interpolation. Okay, if you cannot remember the equation, remember the graph, find the slope at a time. If you cannot remember the graph, copy that equation down to your crib sheet so we can use it. Okay, all right, now that is that. Okay, so practice problem number 3, and this will be problem number 4 in the exam number 1. Okay, I can tell you straight. The problem I have is extremely similar to the problem you see right here. Okay, now one thing I have to ask you to pay attention. I already told you the applied moment, so that is already MU. And in homework number 4, you see some word called factored moment. That is the same as AKA applied moment. Okay. Okay. So AKA required flexure strength. Okay. They're all the same thing, meaning MU, meaning don't need to do no factorization anymore, just MU. That is it, folks. All right, so pay attention to that. Don't want to you guys get confused, start calculating self-weight and all that. You don't have time, and I won't test you these details on calculating self-weight. Usually I won't, okay? And sometimes I even put here, say, you do not need to revise the moment for the self-weight. Meaning, please keep it as it is. Use that for design. Don't make any fussy noise about it, right? Make it more complicated. Okay. All right. So you look at the problem, design for section A. So where is section A? Section A is on the support. It's on the support. Meaning, and this is another trick, right? I have negative moment. I have negative moment. So before you do anything else, you look at this, right? You say, I only learn how to design a singly reinforced tension controlled section with single layer reinforcing bars in tensile zone. That is the simplest form ever, right? It's like you won the lottery already. What else you want, right? So in this case, immediately you start to see, okay, the trick is not about design itself, it's something else, because there's a negative sign. And when you see negative, that means negative bending moment means tensile reinforcement is at top. So no matter what you do, you put the reinforcement at top first, and you put a question mark on that to say, okay, how much now? Isn't it? So I can assure you in the exam, although I said this already, but when you see negative moment, you put reinforcement on top, some people still mess it up in the exam. And I can tell you this, you will have at least 10-point problem on judging where exactly the reinforcement is at. Okay, now in this case, it is negative moment, so the reinforcement is on top. What if it's here in the positive moment region, then it's on the bottom. Okay, so gotta be careful where I am asking you to design. All right, so with that, the rest of the things actually are very easy, right? I have singly reinforced, I have single row, right? And you shouldn't be wrong. And here, in this problem, I was very specific. I said only number 10 bars are used. Couldn't even go around in that, right? But in the actual exam problem, I may be flexible. If I don't mention what type of bar you use, pick a bar that ranging from number 8 to number 10. You shall not go any larger than number 10. Okay, contain yourself between number 8 and number 10. You shall not exceed number 10. Okay, if you start using number 11 bars, we might have some large bar effect. When I say large bar effect is that when the cross section of the bar getting too large, the failure mode can be different. So the yield strength might get compromised. All right, we do not want that. So usually number 10 is fine. Okay, in the real life, people call number 12 and number 14 larger bars, but I just don't like number 11. Okay, number 10 is a safe number. So always remember when you pick design in this class, use number 8 or number 10. Okay, in the practice, something different. Your mentor later will tell you what kind of bar they will use in the design office, what type of building they commonly see. But in this lecture, number 8 and number 10. Okay, all right. So that is 3A. And again, try to do the number and see what you have, right? And I can tell you for number 10 bars, right? You take a look at the 16 inches. Immediately, I can solve the problem in 2 minutes because I know it got to be 3 bars. Just by experience. Okay, 4 bars is stretching it. To put it in, to jam in at 16 inches and put stirrups around it, just too much. 2 bars, too less. Why am I using number 10? Right, I could have used number 9, right, to save myself some hustle carrying the heavy bars in there, right, and to help the bonding side of it. So I can tell you it's 3 bars. But remember, folks, this exam was designed last semester when everybody's COVID, okay, when we have low motivation. So we're trying to make everybody's life easier. And unfortunately, this semester we're back in person, so it's a little bit difficult, okay? So, well, yeah, well, you know, I guess it's a different league now, right? Okay, so truth be told, in this exam, I may not tell you the bars, but I may be kind and tell you the number of bars, but don't guess, all right? Especially don't use table A5 in the detailed calculation. Do the whole thorough calculation, find out the minimum beam width and make sure you can fit the bars in, all right? So last time, 3B, draw the reinforcement obtained from problem 3 on the cross section A, label dimension reinforcing steel bars appropriately. This means when I say appropriate lay, it does not mean, oh, appropriate lay, got to draw a nice circle. No, when I say appropriately, meaning detailed, folks. I want detailed. I want the stirrups, I want the spacing, I want the minimum beam width, calculate out and make sure this is smaller than 60 inches. I want everything. That is the meaning of appropriate lay, meaning more work, okay, more details. All right, so if you draw the right positions, and oh, Bob said put it on top when you have negative, put it at the bottom when you have positive bending moment, fine. I'm just gonna remember this and draw these like that. If the problem was 10 points, if I see this, I give you 5 points for effort. The other rest of the 5 for calculation, you just lost it. So be careful, okay? Do the calculation, show me the detail. I want to know the spacing, okay? That's what matters. All right, now if you have trouble getting the clear cover of the concrete, any clear cover thrown in here is fine, Okay, you can say 1.5, you can say 2-inch, but I require you to put a condition behind it. If it's 1.5, you need to tell me it's an interior exposure from the table or exterior exposure for 2 inches from the table or not. Give me some reason so you can justify your clear cover dimension selection.
Is it safe to assume like the worst conditions?
Yes. Doesn't
3-inch?
matter. Yeah.
Okay.
See, whatever condition you pick doesn't hurt me or bother me. I'm okay. But I just need you to have some reason for your selection. So I know you didn't just throw in some number there. Okay. All right. So you see, we are done. All right. Now I tried this set of problem I gave you guys last semester myself, and I don't remember the number, but I got everything done in 20 minutes. But that's just me, right? So I gave you guys 2 hours and this new problem set, and I worked this morning, I got everything done in 25 minutes. So I think that's a good timing, okay? I feel that you guys should have enough time to run through the problem carefully one time, 1.5 to be precise, but you will not have time to rewrite or rework any of the problems completely. Okay, so my suggestion to you is that take it slow. Okay, don't rush. You will have time. And I essentially showed you the type of problem. I essentially show you the type of problem that you'll be dealing with. And I will not play the game, okay? It will be the identical problem you're seeing here, type. When I say identical, I mean types. Okay, very straightforward and 2 hours. Okay, so for problem, and this part of problem number 5 from problem number 1, I kind of get it broken down, or I relisted this in the problem as a problem 2 in exam number 1. That's what I did differently this time. Okay, but the rest of the problem is the same. So it's essentially 3 problems. Okay, folks, it's not more than last year. Okay, it's not more than last year. So I expect you guys finish in the 1.5 hour, 1 hour, 10 minutes, and really thoroughly, slowly, and got 100 points on this. Now, historically, the average of the first exam is low, but still 80, 79, 80. So not too bad. I used to have 6 to 10 people get hundreds in first exam. Okay, so it's not impossible. All right. And although I'm a very strict professor, but our class average is pretty good on RC design. But for those of you who, if you score lower than 60, you see a lot of me. Okay, but I don't think it will be you guys since you guys are here. Okay, probably those guys who never seen me before. Okay, all right. Any questions, folks? I think I'm done with review. Any question for me?
I have a quick question.
Yes, sir.
So when you say draw the reinforcements with
Yeah.
stirrups, how do you know what size the stirrups are?
You can pick a stirrups yourself. You can pick number 3. You can pick number 4. Since we haven't taught you how to do shear design, that doesn't matter what number you pick. But back it up with your calculation. If you pick number 3, right, you need to show me that number 3 was accounted for when you calculate the minimum beam width.
Okay, so is it possible that we can have different types of answers, like for each, comparing each student's answer could be a little bit different?
Yes, but take a look. We already gave you 16 inches, right? So all I'm asking is to come up with your beam width, minimum beam width, and make sure that is smaller than 16 inches.
Okay.
So it's more like a self-prove or self-check. Right?
All right, got it. Thank
So,
you. Mhm.
yeah, more importantly, I will go through your process and I'll see your understanding of how to calculate the minimum beam width. That's my true intention, okay?
Okay.
Yeah, the number doesn't interest me only, okay? It is the whole process
Okay.
what interests me more. Your understanding interests me, okay?
Okay, thank you.
Yeah, no problem. Any other thing else, folks?
Could you be able to go over how to find the depth of the beam?
The depth of the beam, you're saying?
Yeah, for this problem, problem
For this-
3.
For problem number 3, find the depths of the beam. Yes, sure. So again, I don't have exact numbers, okay, but I can probably help you walk through with you. And give me 1 second. Let me just get this thing. I cannot get it clear. Okay, fine. All right. So read the problem again. The beam width B is restricted to 16 inches. Okay, so that means I have equation I'm going to write on the top of it. Okay, so there was the equation of BD squared greater than or equal to MU divided by phi R. Right? And remember R equal to omega something something, and there's 1 minus 0.59 omega something something. Should be a prime zero, something like that. Okay. Go back to your lecture notes to find out that. Okay, and this is Fletcher resistance factor. Omega is a reinforcing index, and omega is beta1 divided by 4. Okay, if you forgot, go back and check that. Okay, but all I'm saying is these are known. These are known. There's a point phi you can approximate at 0.9 at the get-go. Okay, so here use this equation. You can immediately start to find out D has to be greater than or equal to mu divided by B 16 inches, right? And phi 0.9 and R something, and the whole thing square root. Okay, square root of that. Then you can find the depth of the beam.
Your lecture.
Did I say something different?
So I've got two different equations for DS.
Yeah, these two equations is essentially the
They're
same.
the same.
Yeah,
Okay.
because there's a fish-like, and I learned that yesterday from one of the students. The fish-like symbol alpha is actually the ratio between B and the D,
Oh, okay.
right?
That
So
makes sense.
that's the same actually right now, right? If you look at it.
So is it okay to assume what alpha is if we don't?
If you don't have the width,
the
if you don't have the width, you can assume an alpha. You can
Mhm.
assume half or 1/3. Those are good numbers. But usually in the exam or in a real situation, you will be given width. So in this problem, we tell you 16 inches.
I think you said in class 0.7 at one point.
That's fine too. 0.7 is fine, but that's a little bit stocky.
Yeah, because I think on one of the homeworks we had.
Half, 0.5. Lower, the slender it is.
Okay.
So generally, if we're just gonna use 0.9 is a good one to use.
0.9 is stocky, right? That's for
Right.
phi.
Okay, so
We're
we
talking
want
about alpha.
I'm talking about
Zero
alpha.
point-
Right.
0. Okay,
0.7, 0.5, 0.6, all these are good numbers.
But that's one of those BD squared.
Yes, yes. Okay. So we told you the width is going to be 16 inches, then use that 16 inches. All right. All righty. Any other questions, folks? Online, folks? Anything else, folks? Quiet? Okay. Any of the question from the audience? Okay,
0.7 was my question.
okay,
Oh, number one. We walked in on number
Sure.
2.
okay,
Thank you.
okay. All right, I got a question from chat. Oh, okay, all right, no problem. I see you here. Okay, all righty, folks. If nothing else, I'm going to close out this online section and I will upload this recorded section right away. You'll be able to see it. And I have several people in my office and I'll answer the question from them. And if you're interested in stopping by, I'll stay here till 7:30-ish, okay? All righty, I see you tomorrow, okay? Thanks.
Number one.